of recognizing handwritten digits, whose pixel values get fed into the first layer of the network with 784 neurons, and I've been showing a network with 2 hidden layers having just 16 neurons each, and an output layer of 10 neurons, indicating which digit the network is choosing as its answer. I'm also expecting you to understand gradient descent, as described in the last video, and how what we mean by learning is that we want to find which weights and biases minimize a certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all of these connections, so as to most efficiently decrease the cost. Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is that because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly, beyond the scope of our imaginations, there's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2, while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost, and that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you learn what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation and just step through those effects that each training example is having on the weights and biases. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency we're going to do a little trick later to keep you from needing to hit every single example for every single step. In other case, right now, all we're going to do is focus our attention on one single example, this image of 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. And we can't directly change those activations, we only have influence on the weights and biases. But it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we wanted to classify the image as a 2, we want that third value to get nudged up, while all the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase of that number 2 neuron's activation is in a sense more important than the decrease of the number 8 neuron, but it's already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about a 2. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together wire together idea comes with a couple meaningful asterisks. But, taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listen to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through the same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges. But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand the mechanics for what backpropagation is actually doing. By the way, in practice, it takes computers an extremely long time to add up the influence of every single training example, every single gradient descent step. So here's what's commonly done instead. You randomly shuffle your training data and then divide it into a whole bunch of mini batches, let's say each one having 100 training examples. Then you compute a step according to the mini batch. It's not going to be the actual gradient of the cost function, which depends on all of the training data, not this tiny subset. So it's not the most efficient step downhill, but each mini batch does give you a pretty good approximation, and more importantly, it gives you a significant computational speedup. If you were to plot the trajectory of your network under the relevant cost surface, it would be a little more like a drunk man stumbling aimlessly down a hill but taking quick steps, rather than a carefully calculating man determining the exact downhill direction of each step before taking a very slow and careful step in that direction. This technique is referred to as stochastic gradient descent. There's kind of a lot going on here, so let's just sum it up for ourselves, shall we? Backpropagation is the algorithm for determining how a single training example would like to nudge the weights and biases, not just in terms of whether they should go up or down, but in terms of what relative proportions to those changes cause the most rapid decrease to the cost. A true gradient descent step would involve doing this for all your tens and thousands of training examples and averaging the desired changes that you get. But that's computationally slow, so instead you randomly subdivide the data into these mini batches and compute each step with respect to a mini batch. Repeatedly going through all of the mini batches and making these adjustments, you will converge towards a local minimum of the cost function, which is to say your network is going to end up doing a really good job on the training examples. So with all of that said, every line of code that would go into implementing backprop actually corresponds with something that you have now seen, at least in informal terms. But sometimes knowing what the math does is only half the battle, and just representing the damn thing is where it gets all muddled and confusing. So, for those of you who do want to go deeper, the next video goes through the same ideas that were just presented here, but in terms of the underlying calculus, which hopefully make it a little more familiar as you see the topic in other resources. Before that, one thing worth emphasizing is that for this algorithm to work, and this goes for all sorts of machine learning beyond just neural networks, you need a lot of training data. In our case, one thing that makes handwritten digits such a nice example is that there exists the MNIST database with the hard assumption here is that you've watched part 3. Giving an intuitive walkthrough of the backpropagation algorithm. Here, we get a little bit more formal and dive into the relevant calculus. It's normal for this to be at least a little confusing, so the to regularly pause and ponder certainly applies as much here as anywhere else. Our main goal is to show how people in machine learning commonly think about the chain rule from calculus in the context of networks, which has kind of a different feel from how most introductory calculus courses approach the subject. For those of you uncomfortable with relevant calculus, I do have a whole series on the topic. Let's just start off with an extremely simple network, one where each layer has a single neuron in it. So this particular network is determined by 3 weights and 3 biases, and our goal is to understand how sensitive the cost function is to these variables. That way we know which adjustment to those terms is going to cause the most efficient decrease in the cost function. And we're just going to focus on the connection between the last 2 neurons. Let's label the activation of that last neuron with a superscript L, indicating which layer it's in. So the activation of the previous neuron is a L-1. These are not exponents, they're just a way of indexing what we're talking about, since I want to say subscripts for different indices later on. Now let's say that the value we want this last activation to be for a given training example is y. For example, y might be 0 or 1. So the cost of this simple network for a single training example is AL minus y squared. We'll denote the cost of that one training example as C0. As a reminder, this last activation is determined by a weight, which I'm going to call WL, times the previous neuron's activation, plus some bias, which I'll call BL. And then you pump that through some special nonlinear function like the sigmoid or ReLU. It's actually going to make things easier for us if we give a special name to this weighted sum, like Z, with the same superscript as the relevant activations. So this is a lot of terms, and a way that you might conceptualize it is that the weight, the previous action, and the bias all together are used to compute Z, which in turn lets us compute A, which finally, along with the constant Y, lets us compute the cost. And of course, AL minus 1 is influenced by its own weight and bias and such, but we're not going to focus on that right now. Now all of these are just numbers, right? And it can be nice to think of each one as having its own little number line. Our first goal is to understand how sensitive the cost function is to small changes in our weight, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this del W term, think of it as meaning some tiny nudge to W, like a change by 0.01. And think of this del C term as meaning whatever the resulting nudge to the cost is. What we want is their ratio. Conceptually, this tiny nudge to WL causes some nudge to ZL, which in turn causes some nudge to AL, which directly influences the cost. So we break things up by first looking at the ratio of a tiny change to ZL to this tiny change W. That is, the derivative of ZL with respect to WL. Likewise, you then consider the ratio of the change to AL to the tiny change in ZL that caused it, as well as the ratio between the final nudge to C and this intermediate nudge to AL. This right here is the chain rule, where multiplying together these 3 ratios gives us the sensitivity of C to small changes in WL. So on screen right now, there's kind of a lot of symbols, and take a moment to just make sure it's clear what they all are. because now we're going to compute the relevant derivatives. The derivative of c with respect to al works out to be 2 times al minus y. Notice, this means that its size is proportional to the difference between the network's output and the thing that we want. Want it to be. So if that output was very different, even slight changes tend to have a big impact on the final cost function. The derivative of al with respect to zl is just the derivative of our sigmoid function, or whatever nonlinearity you choose to use. And the derivative of zl with respect to wl, in this case, comes out just to be al minus 1. Now, I don't know about you, but I think it's easy to get stuck head down in the formulas without taking a moment to sit back and remind yourself of what they all actually mean. In the case of this last derivative, the amount that small nudge to the weight influence the last layer depends on how strong the previous neuron is. Remember, this is where that neurons that fire together, wire together idea comes in. And all of this is the derivative with respect to wl only of the cost for a specific single training example. Since the full cost function involves averaging together all those costs across many different training examples, its derivative requires averaging this expression that we found over all training examples. And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to all those weights and biases. But even though that's just one of the main partial derivatives we need, it's more than 50% of the work. The sensitivity to the bias, for example, is almost identical. We just need to change out this del z del w term for a del z del b. And if you look at the relevant formula, that derivative comes out to be 1. Also, and this is where the idea of propagating backwards comes in, you can see how sensitive this cost function is to the activation of the previous layer. Namely, this initial derivative in the chain rule expression, the sensitivity of z to the previous activation, comes out to be the weight, wl. And again, even though we're not going to be able to directly influence that previous layer activation, it's helpful to keep track of, because now we can just keep iterating the same chain rule idea backwards to see how sensitive the cost function is to previous weights and previous biases. And you might think that this is an overly simple example, since all layers just have one neuron, and that things are going to get exponentially more complicated for a real network. But honestly, not that much changes when we give the layers multiple neurons. Really, it's just a few more indices to keep track of. Rather than the activation of a given layer simply being al, it's also going to have a subscript indicating which neuron of that layer it is. Let's go ahead and use the letter k to index the layer l-1, and j to index the layer l. For the cost, again, we look at what the desired output is, but this time we add up the squares of the differences between these last layer activations and the desired output. That is, you take a sum over alj minus yj squared. Since there's a lot more weights, each one has to have a couple more indices to keep track of where it is. So let's call the weight of the edge connecting this kth neuron to the jth neuron WLJK. Those indices might feel a little backwards at first, but it lines up with how you'd index the weight matrix that I talked about in the part 1 video. Just as before, it's still nice to give a name to the relevant weighted sum, like z, so that the activation of the last layer is just your special function, like the sigmoid, applied to z. You can kind of see what I mean, right? Where all of these are essentially the same equations that we had before in the one neuron per layer case, it's just that it looks a little more complicated. And indeed, the chain rule derivative expression describing how sensitive the cost is to a specific weight looks essentially the same. I'll leave it to you to pause and think about each of those terms if you want. What does change here, though, is the derivative of the cost with respect to one of the activations in the layer l-1. In this case, the difference is that the neuron influences the cost function through multiple different paths. That is, on the one hand, it influences al0, which plays a role in the cost function, but it also has an influence on al1, which also plays a role in the cost function. The goal here is simple. Explain what a derivative is. The thing is, though, there's some subtlety to this topic, and a lot of potential for paradoxes if you're not careful. So kind of a secondary goal is that you have an appreciation for what those paradoxes are and how to avoid them. You see, it's common for people to say that the derivative measures an instantaneous rate of change. But when you think about it, that phrase is actually an oxymoron. Change is something that happens between separate points in time. And when you blind yourself to all but just a single instant, there's not really any room for change. You'll see what I mean more as we get into it, but when you appreciate that a phrase like instantaneous rate of change is actually nonsense, I think it makes you appreciate just how clever the fathers of calculus were in capturing the idea that that phrase is meant to evoke, but with a perfectly sensible piece of math, the derivative. As our central example, I want you to imagine a car that starts at some point A, speeds up, and then slows down to a stop at some point B 100 meters away. And let's say it all happens over the course of 10 seconds. That's the setup to have in mind as we lay out what the derivative is. We could graph this motion, letting the vertical axis represent the distance traveled and the horizontal axis represent time. So at each time t, represented with a point somewhere on this horizontal axis, the height of the graph tells us how far the car has traveled in total after that amount of time. It's pretty common to name a distance function like this s of t. I would use the letter d for distance, but that guy already has another full-time job in calculus. Initially, this curve is quite shallow, since the car is slow to start. During that first second, the distance that it travels doesn't really change that much. Then for the next few seconds, as the car speeds up, the distance traveled in a given second gets larger, which corresponds to a steeper slope in this graph. And then towards the end, when it slows down, that curve shallows out again. And if we were to plot the car's velocity in meters per second as a function of time, it might look like this bump. At early times, the velocity is very small. Up to the middle of the journey, the car builds up to some maximum velocity, covering a relatively large distance each second. Then it slows back down towards the speed of 0. And these two curves here are definitely related to each other, right? If you change the specific distance versus time function, you're going to have some different velocity versus time function. And what we want to understand is the specifics of that relationship. Exactly how does velocity depend on a distance versus time function? And to do that, it's worth taking a moment to think critically about what exactly velocity means here. Intuitively, we all might know what velocity at a given moment means. It's just whatever the car's speedometer shows in that moment. And intuitively, it might make sense that the car's velocity should be higher at times when this distance function is steeper, when the car traverses more distance per unit time. But the funny thing is, velocity at a single moment makes no sense. If I show you a picture of a car, just a snapshot in an instant, and I ask you how fast it's going, you'd have no way of telling me. What you'd need are two separate points in time to compare. That way you can compute whatever the change in distance across those times is, divided by the change in time. Right? I mean, that's what velocity is. It's the distance traveled per unit time. So how is it that we're looking at a function for velocity that only takes in a single value of t, a single snapshot in time? It's weird, isn't it? We want to associate individual points in time with a velocity, but actually computing velocity requires comparing two separate points in time. If that feels strange and paradoxical, good. You're grappling with the same conflicts that the fathers of calculus did. And if you want a deep understanding for rates of change, not just for a moving car, but for all sorts of things in science, you're going to need to resolve this apparent paradox. First, I think it's best to talk about the real world, and then we'll go into a purely mathematical one. Let's think about what the car's speedometer is probably doing. At some point, say 3 seconds into the journey, the speedometer might measure how far the car goes in a very small amount of time, maybe the distance traveled between 3 seconds and 3.01 seconds. Then it can compute the speed in meters per second as that tiny distance traversed in meters divided by that tiny time, 0.01 seconds. That is, a physical car just sidesteps the paradox and doesn't actually compute speed at a single point in time. It computes speed during a very small amount of time. So let's call that difference in time dt, which you might think of in this case as 0.01 seconds, and let's call that resulting difference in distance ds. So the velocity at some point in time is ds divided by dt, the tiny change in distance over the tiny change in time. Graphically, you can imagine zooming in on some point of this distance versus time graph above t equals 3. That dt is a small step to the right, since time is on the horizontal axis, and that ds is the resulting change in the height of the graph, since the vertical axis represents the distance traveled. So ds divided by dt is something you can think of as the rise over run slope between two very close points on this graph. Of course, there's nothing special about the value t equals 3. We could apply this to any other point in time, so we consider this expression ds over dt to be a function of t, something where I can give you a time t, and you can give me back the value of this ratio at that time, the velocity as a function of time. So for example, when I had the computer draw this bump curve here, the one representing the velocity function, here's what I had the computer actually do. First, I chose a small value for dt, I think in this case it was 0.01. Then I had the computer look at a whole bunch of times t between 0 and 10, and compute the distance function s at t plus dt, and then subtract off the value of that function at t. In other words, that's the difference in the distance traveled between the given time t and the time 0.01 seconds after that. Then you can just divide that difference by the change in time dt, and that gives you velocity in meters per second around each point in time. So with a formula like this, you can give a computer any curve representing any distance function s of t, and you can figure out the curve representing velocity. So now would be the time to pause, reflect, make sure that this idea of relating distance to velocity by looking at tiny changes makes sense, because what we're going to do is tackle the paradox of the derivative head on. This idea of ds over dt, a tiny change in the value of the function s divided by the tiny change in the input it caused it, that's almost what a derivative is. And even though a car speedometer will actually look at a concrete change in time like 0.01 seconds, and even though the drawing program here is looking at an actual concrete change in time, in pure math, the derivative is not this ratio of ds dt for a specific choice of dt. Instead, it's whatever that ratio approaches as your choice for dt approaches 0. Luckily, there is a really nice visual understanding for what it means to ask what this ratio approaches. Remember, for any specific choice of dt, this ratio ds dt is the slope of a line passing through two separate points on the graph, right? Well, as dt approaches 0, and as those 2 points approach each other, the slope of the line approaches the slope of the line that's tangent to the graph at whatever point t we're looking at. So the true, honest to goodness, pure math derivative is not the rise over run slope between two nearby points on the graph. It's equal to the slope of a line tangent to the graph at a single point. Now, notice what I'm not saying. I'm not saying that the derivative is whatever happens when dt is infinitely small, whatever that would mean. Nor am I saying that you plug in 0 for dt. This dt is always a finitely small, non-zero value. It's just that it approaches 0 is all. I think that's really clever. Even though change in an instant makes no sense, this idea of letting dt approach 0 is a really sneaky backdoor way to talk reasonably about the rate of change at a single point in time. Isn't that neat? It's kind of flirting with the paradox of change in an instant without ever needing to actually touch it. And it comes with such a nice visual intuition too, as the slope of a tangent line to a single point on the graph. And because change in an instant still makes no sense, I think it's healthiest for you to think of the slope not as some instantaneous rate of change, but instead as the best constant approximation for a rate of change around a point. By the way, it's worth saying a couple words on notation here. Throughout this video, I've been using dt to refer to a tiny change in t with some actual size, and ds to refer to the resulting change in s, which again has an actual size. And this is because that's how I want you to think about them. But the convention in calculus is that whenever you're using the letter d like this, you're kind of announcing your intention that eventually you're going to see what happens as dt approaches 0. For example, the honest to goodness pure math derivative is written as ds divided by dt, even though it's technically not a fraction per se, but whatever that fraction approaches for smaller and smaller nudges in t. I think a specific example should help here. You might think that asking about what this ratio approaches for smaller and smaller values would make it much more difficult to compute, but weirdly, it kind of makes things easier. Let's say that you have a given distance versus time function that happens to be exactly t cubed. So after 1 second, the car has traveled 1 cube equals 1 meters. After 2 seconds, it's traveled 2 cubed, or 8 meters, and so on. Now what I'm about to do might seem somewhat complicated, but once the dust settles, it really is simpler. And more importantly, it's the kind of thing that you only ever have to do once in calculus. Let's say you wanted to compute the velocity, ds divided by dt, at some specific time, like t equals 2. And for right now, let's think of dt as having an actual size, some concrete nudge. We'll let it go to 0 in just a bit. The tiny change in distance between 2 seconds and 2 plus dt seconds, well, that's s of 2 plus dt minus s of 2. And we divide that by dt. Since our function is t cubed, that numerator looks like 2 plus dt cubed minus 2 cubed. And this is something we can work out algebraically. Again, bear with me. There's a reason that I'm showing you the details here. When you expand that top, what you get is 2 cubed plus 3 times 2 squared dt plus 3 times 2 times dt squared plus dt cubed, and all of that is minus 2 cubed. Now there's a lot of terms, and I want you to remember that it looks like a mess, but it does simplify. Those 2 cubed terms, they cancel out. And then everything remaining here has a dt in it. And since there's a dt on the bottom there, many of those cancel out as well. What this means is that the ratio ds divided by dt has boiled down into 3 times 2 squared plus, well, 2 different terms that each have a dt in them. So if we ask what happens as dt approaches 0, representing the idea of looking at a smaller and smaller change in time, we can just completely ignore those other terms. By eliminating the need to think about a specific dt, we've actually eliminated a lot of the complication in the full expression. So what we're left with is this nice clean 3 times 2 squared. You can think of that as meaning that the slope of a line tangent to the point at t equals 2 of this graph is exactly 3 times 2 squared, or 12. And of course, there's nothing special about the time t equals 2. We can more generally say that the derivative of t cubed as a function of t is 3 times t squared. Now take a step back, because that's beautiful. The derivative is this crazy complicated idea. We've got tiny changes in distance over tiny changes in time, but instead of looking at any specific one of those, we're talking about what that thing approaches. I mean, that's a lot to think about. And yet what we've come out with is such a simple expression, 3 times t squared. And in practice, you wouldn't go through all this algebra each time. Knowing that the derivative of t cubed is 3t squared is one of those things that all calculus students learn how to do immediately without having to read about it each time. And in the next video, I'm going to show you a nice way to think about this and a couple other derivative formulas in really nice geometric ways. But the point I want to make by showing you all the algebraic guts here is that when you consider the tiny change in distance caused by a tiny change in time for some specific value of dt, you have kind of a mess. But when you consider what that ratio approaches as dt approaches 0, it lets you ignore much of that mess, and it really does simplify the problem. That right there is kind of the heart of why calculus becomes useful. Another reason to show you a concrete derivative like this is that it sets the stage, for example, of the kind of paradoxes that come about if you believe too much in the illusion of instantaneous rate of change. So think about the actual car traveling according to this t cubed distance function, and consider its motion at the moment t equals 0, right at the start. Now ask yourself whether or not the car is moving at that time. On one hand, we can compute its speed at that point using the derivative. Now that we've seen what a derivative means and what it has to do with rates of change, the next step is to learn how to actually compute these guys. As in, if I give you some kind of function with an explicit formula, you want to be able to find what the formula for its derivative is. Maybe it's obvious, but I think it's worth stating explicitly why this is an important thing to be able to do. Why much of calculus students' time ends up going towards grappling with derivatives of abstract functions rather than thinking about concrete rate of change problems. It's because a lot of real-world phenomena, the sort of things that we want to use calculus to analyze, are modeled using polynomials, trigonometric functions, exponentials, and other pure functions like that. So if you build up some fluency with the ideas of rates of change for those kinds of pure abstract functions, it gives you a language to more readily talk about the rates at which things change in concrete situations that you might be using calculus to model. But it is way too easy for this process to feel like just memorizing a list of rules. And if that happens, if you get that feeling, it's also easy to lose sight of the fact that derivatives are fundamentally about just looking at tiny changes to some quantity and how that relates to a resulting tiny change in another quantity. So in this video and in the next one, my aim is to show you how you can think about a few of these rules intuitively and geometrically. And I really want to encourage you to never forget that tiny nudges are at the heart of derivatives. Let's start with a simple function, like f of x equals x squared. What if I asked you its derivative? That is, if you were to look at some value x, like x equals 2, and compare it to a value slightly bigger, just dx bigger, what's the corresponding change in the value of the function, df? And in particular, what's df divided by dx, the rate at which this function is changing per unit change in x? As a first step for intuition, we know that you can think of this ratio df dx as the slope of a tangent line to the graph of x squared. And from that, you can see that the slope generally increases as x increases. At 0, the tangent line is flat, and the slope is 0. At x equals 1, it's something that's steeper. At x equals 2, it's steeper still. But looking at graphs isn't generally the best way to understand the precise formula for a derivative. For that, it's best to take a more literal look at what x squared actually means. And in this case, let's go ahead and picture a square whose side length is x. If you increase x by some tiny nudge, some little dx, what's the resulting change in the area of that square? That slight change in area is what df means in this context. It's the tiny increase to the value of f of x equals x squared caused by increasing x by that tiny nudge dx. Now you can see that there's three new bits of area in this diagram, two thin rectangles and a minuscule square. The two thin rectangles each have side lengths of x and dx, so they account for 2 times x times dx units of new area. For example, let's say x was 3 and dx was 0.01, then that new area from these two thin rectangles would be 2 times 3 times 0.01, which is 0.06, about 6 times the size of dx. That little square there has an area of dx squared, but you should think of that as being really tiny, negligibly tiny. For example, if dx was 0.01, that would be only 0.0001. And keep in mind, I'm drawing dx with a fair bit of width here just so we can actually see it, but always remember, in principle, dx should be thought of as a truly tiny amount. And for those truly tiny amounts, a good rule of thumb is that you can ignore anything that includes a dx raised to a power greater than 1. That is, a tiny change squared is a negligible change. What this leaves us with is that df is just some multiple of dx, and that multiple, 2x, which you could also write as df nudge, some little dx, what's this function is changing per unit change in x. As a first step for intuition, we know that you can think of this ratio df dx as the slope of a tangent line to the graph of x squared. And from that, you can see that the slope generally increases as x increases. At 0, the tangent line is flat, and the slope is 0. At x equals 1, it's something that's steeper. At x equals 2, it's steeper still. But looking at graphs isn't generally the best way to understand the precise formula for a derivative. For that, it's best to take a more literal look at what x squared actually means. And in this case, let's go ahead and picture a square whose side length is x. If you increase x by some tiny nudge, some little dx, what's the resulting change in the area of that square? That slight change in area is what df means in this context. It's the tiny increase to the value of f of x equals x squared caused by increasing x by that tiny nudge dx. Now you can see that there's three new bits of area in this diagram, two thin rectangles and a minuscule square. The two thin rectangles each have side lengths of x and dx, so they account for 2 times x times dx units of new area. For example, let's say x was 3 and dx was 0.01, then that new area from these two thin rectangles would be 2 times 3 times 0.01, which is 0.06, about 6 times the size of dx. That little square there has an area of dx squared, but you should think of that as being really tiny, negligibly tiny. For example, if dx was 0.01, that would be only 0.0001. And keep in mind, I'm drawing dx with a fair bit of width here just so we can actually see it, but always remember, in principle, dx should be thought of as a truly tiny amount. And for those truly tiny amounts, a good rule of thumb is that you can ignore anything that includes a dx raised to a power greater than 1. That is, a tiny change squared is a negligible change. What this leaves us with is that df is just some multiple of dx, and that multiple, 2x, which you could also write as df divided by dx, is the derivative of x squared. For example, if you were starting at x equals 3, then as you slightly increase x, the rate of change in the area per unit change in length added, dx squared over dx, would be 2 times 3, or 6. And if instead you were starting at x equals 5, then the rate of change would be 10 units of area per unit change in x. Let's go ahead and try a different simple function, f of x equals x cubed. This is going to be the geometric view of the stuff that I went through algebraically in the last video. What's nice here is that we can think of x cubed as the volume of an actual cube, whose side lengths are x. And when you increase x by a tiny nudge, a tiny dx, the resulting increase in volume is what I have here in yellow. That represents all the volume in the cube with side lengths x plus dx that's not already in the original cube, the one with side length x. It's nice to think of this new volume as broken up into multiple components, but almost all of it comes from these three square faces. Or, said a little more precisely, as dx approaches 0, those three squares comprise a portion closer and closer to 100% of that new yellow volume. Each of those thin squares has a volume of x squared times dx, the area of the face times that little thickness dx. So in total, this gives us 3x squared dx of volume change. And to be sure, there are other slivers of volume here along the edges and the tiny one in the corner, but all of that volume is going to be proportional to dx squared, or dx cubed, so we can safely ignore them. Again, this is ultimately because they're going to be divided by dx. And if there's still any dx remaining, then those terms aren't going to survive the process of letting dx approach 0. What this means is that the derivative of x cubed, the rate at which x cubed changes per unit change of x, is 3 times x squared. What that means in terms of graphical intuition is that the slope of the graph of x cubed at every single point x is exactly 3x squared. And reasoning about that slope, it should make sense that this derivative is high on the left, and then 0 at the origin, and then high again as you move to the right. But just thinking in terms of the graph would never have landed us on the precise quantity 3x squared. For that, we have to take a much more direct look at what x cubed actually means. Now, in practice, you wouldn't necessarily think of the square every time you're taking the derivative of x squared, nor would you necessarily think of this cube whenever you're taking the derivative of x cubed. Both of them follow a pretty recognizable pattern for polynomial terms. The derivative of x to the fourth turns out to be 4x cubed, the derivative of x to the fifth is 5x to the fourth, and so on. Abstractly, you write this as the derivative of x to the n for n power n is n times x to the n minus 1. This right here is what's known in business as the power rule. In practice, we all quickly just get jaded and think about this symbolically, as the exponent hopping down in front, leaving behind one less than itself, rarely pausing to think about the geometric delights that underlie these derivatives. That's the kind of thing that happens when these tend to fall in the middle of much longer computations. But rather than chucking it all off to symbolic patterns, let's just take a moment and think about why this works for powers beyond just 2 and 3. When you nudge that input x, increasing it slightly to x plus dx, working out the exact value of that nudged output would involve multiplying together these n separate x plus dx terms. The full expansion would be really complicated, but part of the point of derivatives is that most of that complication can be ignored. The first term in your expansion is x to the n. This is analogous to the area of the original square, or the volume of the original cube from our previous examples. For the next terms in the expansion, you can choose mostly x's with a single dx. Since there are n different parentheticals from which you could have chosen that single dx, this gives us n separate terms, all of which include n minus 1 x's times a dx, giving a value of x to the power n minus 1 times dx. This is analogous to how the majority of the new area in the square came from those two bars, each with area x times dx, or how the bulk of the new volume in the cube came from those three thin squares, each of which had a volume of x squared times dx. There will be many other terms of this expansion, but all of them are just going to be some multiple of dx squared, so we can safely ignore them. And what that means is that all but a negligible portion of the increase in the output comes from n copies of this x to the n minus 1 times dx. That's what it means for the derivative of x to the n to be n times x to the n minus 1. And even though, like I said, in practice, you'll find yourself performing this derivative quickly and symbolically, imagining the exponent hopping down to the front, every now and then, it's nice to just step back and remember why these rules work. Not just because it's pretty, and not just because it helps remind us that math actually makes sense and isn't just a pile of formulas to memorize, but because it flexes that very important muscle of thinking about derivatives in terms of tiny nudges. As another example, think of the function f of x equals 1 divided by x. Now, on the one hand, you could just blindly try applying the power rule, since 1 divided by x is the same as writing x to the negative 1. That would involve letting the negative 1 hop down in front, leaving behind 1 less than itself, which is negative 2. But let's have some fun, and see if we can reason about this geometrically, rather than just plugging it through some formula. The value 1 over x is asking what number multiplied by x equals 1. So here's how I'd like to visualize it. Imagine a little rectangular puddle of water sitting in 2 dimensions, whose area is 1. And let's say that its width is x, which means that the height has to be 1 over x, since the total area of it is 1. So if x was stretched out to 2, then that height is forced down to 1/2. And if you increase x up to 3, then the other side has to be squished down to 1/3. This is a nice way to think about the graph of 1 over x, by the way. If you think of this width x of the puddle as being in the xy plane, then that corresponding output, 1 divided by x, the height of the graph above that point, is whatever the height of your puddle has to be to maintain an area of 1. So with this visual in mind, for the derivative, imagine nudging up that value of x by some tiny amount, some tiny dx. How must the height of this rectangle change so that the area of the puddle remains constant at 1? That is, increasing the width by dx adds some new area to the right here. So the puddle has to decrease in height by some d1 over x so that the area lost off of that top cancels out the area gained. You should think of that d1 over x as being a negative amount, by the way, since it's decreasing the height of the rectangle. And you know what? I'm going to leave the last few steps here for you to pause and ponder and work out an ultimate expression. And once you reason out what d of 1 over x divided by dx should be, I want you to compare it to what you would have gotten if you had just blindly applied the power rule purely symbolically to x to the negative 1. And while I'm encouraging you to pause and ponder, here's another fun challenge if you're feeling up to it. See if you can reason through what the derivative of the square root of x should be. To finish things off, I want to tackle one more type of function, trigonometric functions. And in particular, let's focus on the sine function. So for this section, I'm going to assume that you're already familiar with how to think about trig functions using the unit circle, the circle with a radius 1 centered at the origin. For a given value of theta, like say 0.8, you imagine yourself walking around the circle, starting from the rightmost point, until you've traversed that distance of 0.8 in arc length. This is the same thing as saying that the angle right here is exactly theta radians, since the circle has a radius of 1. Then what sine of theta means is the height of that point above the x-axis. And as your theta value increases, and you walk around the circle, your height bobs up and down between negative 1 and 1. So when you graph sine of theta versus theta, you get this wave pattern, the quintessential wave pattern. And just from looking at this graph, we can start to get a feel for the shape of the derivative of the sine. The slope at 0 is something positive, since sine of theta is increasing there. And as we move to the right and sine of theta approaches its peak, that slope goes down to 0. Then the slope is negative for a little while the sine is decreasing, before coming back up to 0 as the sine graph levels out. And as you continue thinking this through and drawing it out, if you're familiar with the graph of trig functions, you might guess that this derivative graph should be exactly cosine of theta, since all the peaks and valleys line up perfectly with where the peaks and valleys for the cosine function should be. And spoiler alert, the derivative is in fact the cosine of theta. But aren't you a little curious about why it's precisely cosine of theta? I mean, you can have all sorts of functions with peaks and valleys at the same points that have roughly the same shape, but who knows, maybe the derivative of sine could have turned out to be some entirely new type of function that just happens to have a similar shape. Well, just like the previous examples, a more exact understanding of the derivative requires looking at what the function actually represents, rather than looking at the graph of the function. So think back to that walk around the unit circle, having traversed an arc with length theta and thinking about sine of theta as the height of that point. Now zoom into that point on the circle and consider a slight nudge of d theta along their circumference, a tiny step in your walk around the unit circle. How much does that tiny step change the sine of theta? How much does this increased d theta of arc length increase the height above the x-axis? Well, zoomed in close enough, the circle basically looks like a straight line in this neighborhood. So let's go ahead and think of this right triangle, where the hypotenuse of that right triangle represents the nudge d theta along the circumference, and that left side here represents the change in height, the resulting d sine of theta. Now this tiny triangle is actually similar to this larger triangle here, with the defining angle theta, and whose hypotenuse is the radius of the circle with length 1. Specifically, this little angle right here is precisely equal to theta radians. Now think about what the derivative of sine is supposed to mean. It's the ratio between that d sine of theta, the tiny change to the height, divided by d theta, the tiny change to the input of the function. And from the picture, we can see that that's the ratio between the length of the side adjacent to the angle theta divided by the hypotenuse. Well, let's see, adjacent divided by hypotenuse, that's exactly what the cosine of theta means. That's the definition of the cosine. So this gives us two different really nice ways of thinking about how the derivative of sine is cosine. One of them is looking at the graph and getting a loose feel for the shape of things based on thinking about the slope of the sine graph at every single point. And the other is a more precise line of reasoning, looking at the unit circle itself. For those of you that like to pause and ponder, see if you can try a similar line of reasoning to find what the derivative of the cosine of theta should be. In the next video, I'll talk about how you can take derivatives of functions who combine simple functions like these ones, either as sums or products or function compositions, things like that. And similar to this video, the goal is going to be to understand each one geometrically in a way that makes it intuitively reasonable and somewhat more. In the last videos, I talked about the derivatives of simple functions, and the goal was to have a clear picture or intuition to hold in your mind that actually explains where these formulas come from. But of course, most of the functions you deal with in modeling the world involve somehow mixing or combining or tweaking these simple functions in some other way. So our natural next step is to understand how you take derivatives of more complicated combinations. And again, I don't want these to be something to memorize. I want you to have a clear picture in mind for where each one comes from. Now, this really
Hello everyone, a very good afternoon.
So at a very high level, what does math have to do with then go and put 1 in for b? So I didn't fall for this trick. You did not fall for this trick, but I taught these classes before and I've seen places. To remind you of our overall structure, we're figuring out what math has to do with machine learning. And even though all programming involves math at some level, machine learning is a particular kind of programming. It's programming by optimization. Rather than telling a computer exactly what we want it to do, we tell the computer, here's what it means to get better at this task. It's very numerical rather than like programming where you just write stuff. And so we really need math for this type of programming in order to understand that optimization process. So we already talked about the objects that were being optimized, the first way that optimization and machine learning intersect. When we talked about linear algebra, there we talked about arrays, which sort of represent our data and our models. These are the things that go into our optimization process. Our parameters, we'll see, are often thought of as arrays, the things that determine how our model behaves, the equivalent of our code, effectively. And so all of that fell under the aegis of linear algebra. Now we're going to talk about how we optimize with calculus. Calculus helps us make tiny changes in order to iteratively, slowly improve the behavior of our computer programs with machine learning. We still won't cover what it is that we're optimizing, so we're really leaving the meat of it for the third session where we talk about probability and statistics, because it turns out what we want to do is reduce surprise or reduce uncertainty. Our models. But today we will focus instead on how we optimize with calculus. So let's dive in. So the takeaways for today are that calculus is approximation with linear maps, and that calculus helps us incrementally optimize. The first point indicates a connection to what we talked about in linear algebra, which we're going to really chew on today. But then one point which we will hopefully but not definitely get to is that calculus has been automated. Calculus can be done automatically in computers nowadays. Vector calculus is at the center of machine learning. So I think most folks will probably have taken a class on calculus with a single variable, derivatives of functions with a single variable. Vector calculus does the same thing, but instead it's with vectors, with arrays, with matrices as the arguments to the functions. And so some examples of where vector calculus shows up, you may have, if you've done linear regression before, you got an exact solution. Those exact solutions are derived using calculus. So the actual calculation isn't done using calculus, but the derivation uses calculus. If you've ever calculated eigenvectors and eigenvalues, that is typically done with, if you want to calculate them iteratively, it's done with a method that is justified using calculus. And so the explanation for why this works uses calculus. Then the algorithms of gradient descent and back propagation, where the former is a generic term and the latter is a specific term for neural networks. These algorithms are used to optimize machine learning algorithms, and they are calculus-based. And so the usual thing you'll hear is that vector calculus combines linear algebra and calculus, where linear algebra is algebra for solving equations with vectors and matrices instead of just numbers, and calculus is a collection of methods for studying rates of change and areas. But we've already seen that the former is not necessarily the best way to think about linear algebra for machine learning. The linear algebra is instead the study of functions that can be represented by arrays, aka linear maps, as we talked about last time. This time, we'll talk about a different way to think about calculus. Calculus, at least derivative calculus, which is our primary concern, is the study of methods for approximating functions with linear maps. So rather than the function being exactly the same as something linear, we're going to approximate the function with something linear. And we're going to take a slightly different tack than the usual way of covering it, of defining it. We're going to use a slightly different definition of the derivative. At least the end result is the same, but the definition is different. And in mathematics, the way we write our definitions is really important, even if the final object is equivalent. And so basically what we're going to do is we're going to define the derivative using linear maps, and that's going to make vector calculus a lot easier when it comes time. And the three benefits are that we're going to end up with a single style for thinking about gradients, aka derivatives of single variable vector and matrix functions. We're going to drop indices from all of our calculations, so it's not going to be this big thicket of i's and j's and k's as sometimes happens when you do vector calculus. And we'll also get a chance to use something called the little o notation instead of limits, which has connections to the big O notation from computer science, and I think it's just a little bit more intuitive and easier to work with. So let's talk about how this works for single variable functions. These are the functions you would come across in a first calculus sequence. We'll call the calculus A, B, and D in the American schooling system. The standard definition of the derivative emphasizes limits. It says that the derivative is the limit of a ratio, and that ratio is between change in output and change in input. We take a function, we're trying to find the derivative of that function, and what we do is we look at the difference between how it behaves at one point, how it behaves at another point, and we divide by how far away those points are. And then we make that change in input smaller. We move the 2 points we're querying closer together. We imagine making that infinitely small. The mathematics of limits gives us an answer to what this ratio limits to, and that is what we call the derivative. And there are some useful things about thinking that way, but I want to emphasize a slightly different way of thinking about it, which is we're going to instead think in terms of approximation. So the derivative is going to show up as a function that helps us approximate other functions. We're still thinking about, okay, what if I imagine input at one point versus input at another point? But instead we're saying the value at another point, epsilon away from my query point x, is equal to the original point. So this is setting our sort of baseline, plus some function of x, we can do whatever we want, times epsilon. So now we're multiplying these two things together, and then plus something smaller. So just for now, just think of little o of epsilon as meaning this thing is really small. At least it is smaller than epsilon. Then we call that function f prime the derivative. So one way to think about this is that if we can always approximate the behavior of f near x, so f at x plus epsilon for various different points of epsilon, we can approximate that with a line passing through f of x with slope f prime of x. Then we call the function that gives us the slope the derivative. Now this right here is the definition of a line, right? We have an intercept here, we have a slope here, and then we have a variable here. Epsilon is a variable now. This is often b for bias m. I don't know why that's the slope thing in x, so y equals mx plus b is the way that equation is often written. This is the equation for a line, and it doesn't give us the exact value of f of x plus epsilon. That would be too good. That would be too easy. In general, it gives us something that's off by a little bit, and the amount it's off by is given by this little o of epsilon term, which could be lots of different functions of epsilon. It could be epsilon squared, it could be e to the minus epsilon, it could be anything that's really small when epsilon is really, really small. So the function we are using to approximate f near a point is linear, right? F prime of x times epsilon. This is, even though f prime of x can be anything, the way it interacts with epsilon, the way it interacts with our variable is multiplicative. And so this function we're using to approximate f near the point x is linear, and therefore can always be represented by an array. Right now it's an array with one element, so this isn't that interesting, right? And the way we use the array is we're basically doing a dot product. We're taking one number here, multiplying them together, and adding up the results. We get one number. You know, this maybe doesn't seem that useful of a use of our linear algebra analogy yet, but watch this space for the next example. I think it's maybe useful to have a picture. I have this function, this curve here. I actually just drew this in Google Slides, so I don't know how to calculate values of this function at other points. But I know that this is its value at one point. And the question is, okay, how do I figure out what its value is at another point? So I can't query this function at all. So one way to figure out what its value at another point is to approximate it. And how are we going to approximate it? There are lots of different ways that we could approximate a function, just tons. But the way we're going to approximate it is by using local, like around a particular point, linear, straight line approximations. So they won't give us exact answers, they'll give us approximations, but they'll be pretty good. If you look at this gold line here that represents our approximation, it actually stays pretty close to the gray line across this region here. The approximation is pretty valid across the region where I'm bringing my pointer here. We have our point in gray, f of x, that's where we start. It's also the 0 point of our approximation. When epsilon is 0, that's what our guess is. F of x equals f of x. Great, that's a good sign. And then as we move away, we use the slope of this line times epsilon to get our new point. So then our approximation is the point I'm indicating with my bright red indicator there, my little laser pointer. And that value is not exactly right. The actual answer is this bigger red circle here, but the difference between them is actually quite small, and that's that purple, tiny little purple block in between the yellow and the red point. That's our O of epsilon term. So if the value at a point epsilon away is this point's value plus this linear function of epsilon plus something really small that we can maybe ignore if we're squinting, we call that function, that gold function there, the derivative. So here's how this definition gets used. I want to give you a sense for how this would get used to define or compute derivatives as opposed to the way it's normally done. So consider the function x squared. This function, we'll see its derivative actually. I won't spoil it just in case you don't recall recall or haven't learned the derivative of x squared. So x squared is equal to x times x. Let's calculate a derivative for the function x squared just using our definition. What we do is we write out the left-hand side of our definition, f of x plus epsilon, right? So this is saying, okay, what is the value of our function at this other point? And then we just move around our symbols, we play some algebra games until we can get it to look like the right-hand side of our definition. And then all those pieces, we just match them. So let me show you how that works. X plus epsilon times x plus epsilon, that's what f of x is, right? It's x squared. And so the input gets squared, our input is now x plus epsilon. So then we just expand that out, x squared plus x times epsilon plus epsilon times x plus epsilon squared. We do a little bit of rearrangement. This is just two copies of x times epsilon. Let's take a look at what we got. Well, we got x squared, that's our f of x, right? This is what I mean by pattern matching. We match each component of this here to each component of this here. Then we've also got this nice thing here where we've got operator matches our definitions expression. So epsilon here, it's interacting with x only by multiplication, right? It's interacting with our f prime of x term only through multiplication. So that counts as our sort of linear term in epsilon. And then we've got this term here, epsilon squared. Now you might think of squaring something as making it bigger because we normally think of numbers bigger than 1, right? 2 squared is bigger than 2, it's 4. 100 squared is 10,000. But for 1 over 100, 1 over 100 squared is 1 over 10,000. So squaring actually, just like it makes things really much bigger as numbers get bigger, it actually makes things much, much smaller as numbers get closer to 0. So epsilon squared actually counts as something that is smaller than epsilon. That's this little o of epsilon term. So that's our final piece. And now we've done it. We've pattern matched this expression here to our definition. And so the derivative of x squared is 2x. The nice thing here is we do have to be able to reason about this little o term here, but I find that substantially easier than doing this whole thing underneath a limit. Limits, it's always a little bit unclear to me what's allowed and what's not allowed under a limit. And in fact, physicists and mathematicians often fight about which limits are appropriate to take. It's useful technology to have limits around, but I like to focus on specific examples where I can be very clear that what I'm doing is correct. So let's talk about what little o is. It is indeed a type of limit and a limit of ratios. So the idea that limits of ratios are important for calculus is not gone. It's just been given a really nice API is how I think about it. Little o is a nice abstraction, a nice thing built out of limits that's easier to work with than the thing itself, like Python is built out of C. So a term is little o of epsilon if it gets smaller much faster than epsilon does. That's the intuitive way of framing it. So little o of epsilon means as you get close to 0, something is little o of epsilon if it gets closer to 0 much faster than epsilon does, which has a specific mathematical definition, which is that if the limit as x goes to 0 of f of x over g of x is 0, which means g of x, the bottom of the ratio, is bigger than the top of the ratio. Then we can replace f of x with little o of g of x. So often g will just be the identity function. Like previously we had little o of epsilon as the inner argument there. So that says that this function of the variable is smaller than the variable itself. If we have f of epsilon over epsilon has its limit being 0. And this means that for a small enough epsilon, anything little o of epsilon can safely be ignored. So here are a couple of examples. So some terms that are little o of epsilon. So 0 is little o of epsilon. If I look, the limit as x goes to 0 of 0 over x, that's just going to be 0. If I look at x squared, so the limit of x squared over x, that's going to be x squared divided by x, that's just x. Limit as x goes to 0 is 0. Kx squared, I can multiply x squared by something, and that doesn't change the argument I just gave. The limit of k times x as x goes to 0 remains 0. So all those terms are little o of x. Some things on the right that are not little o of x, so 1 over x, so a constant value is not little o of x. It's if our approximation will always be off by 1, right? So intuitively that makes sense, but by definition, what that means is the limit as x goes to 0 of 1 over x, that is actually infinite rather than 0. X is not little o of x. X over x, that's just 1. The limit of x goes to 0 of 1 is 1. And multiplying that by something doesn't change it. There's some useful rules, like you can add them together. If I have two little o terms, the sum of them is still little o, but I won't go fully into the details because it's actually not that important that you become really good at calculating derivatives. It's more important that you have a sense intuitively for what these pieces mean and what the derivative is, which is something that is off by a little o term. And so the reason why I like this is because it's really similar to something that I end up using and thinking about when I'm writing computer code, which is big O notation for computer science. Let's just talk about how fast algorithms are while abstracting away a bunch of irrelevant details about the exact implementation of it and things about that might be different across CPUs or whatever. So the idea is something that's big O of n is faster than something that's big O of n squared, which is much faster than something that's big O of 2 to the n for a big enough input. Similarly, little o lets us talk about the best linear approximation while abstracting away exactly how good or bad that approximation is. When you're doing the limit, like the classical limit approach to studying calculus, these two things get mixed up together, and you always need to both measure how good the linear approximation is exactly and produce the correct value for it. But with little o notation, with the Fréchet derivative style, that's the name for this definition of derivative, then you can split those two things apart. Little o and big O, they're called Landau symbols. And so if you want to look up more about these and see a little bit more about how they function. So now let's use that view of what calculus is doing in order to understand our optimization process in machine learning. So when we optimize in machine learning, we optimize through many tiny changes, almost always. There are a few times where we optimize by just doing it all at once, but we almost always optimize by making many tiny changes. What we want to do in machine learning is we want to update the parameter values of a model to make it perform better. So usually in machine learning, effectively our program for doing the task that we want to do is specified by a vector. And then we can calculate how well it's doing with this function called the loss function. So it takes in the vector, it usually applies some function to a bunch of data, sort of checks, maybe it's predicting something, one data value based off another data value, maybe it's compressing data. There's lots of things we can do with machine learning, but we always need to be able to score how well we are doing. And that's the function f here. And we want to make that value, usually it's golf rules where lower is better. And so I want to choose new parameters such that the value of this function goes down. It'd be great if we just knew like all the values of that. If we could just look at the plot of the function and say, oh, that would be the best value over there. But we can't do that in general because there are 100-dimensional vectors, million-dimensional vectors, trillion-dimensional vectors nowadays in machine learning. So we'll never ever be able to look at them and solve it. And we can't even actually know what the value of the function is going to be at some other point. We have to calculate values of this function. It's often extremely expensive. We have to calculate calculate for some models, we have to feed gigabytes of data into them to know what the values can be. So we want to try and avoid that calculation as much as possible. So what we're going to do is we're going to use linear approximations to that function. So we're going to make my best linear guess to what the function will be somewhere else. And we want that to say, oh, your performance will be better, the value of f will be smaller. So we're going to choose new parameters to make the best linear guess go down as fast as possible. And so we'll see in a second that the way to do that is to pick our value of epsilon, our change in our parameters. We pick it to point basically in the opposite direction. That makes this linear term as negative as possible. Then the question is, how big do we make epsilon? Do we make epsilon really big because we want to make a big change? Well, no, because we know that this is just a linear guess, right? We shouldn't change too much. And that's coming from this last term here, this purple term, saying the bigger we make our change, the wronger we should expect to be about whether our machine learning model is actually performing better or not. And reading all that off leads us directly to the algorithm of gradient descent. So it says, for our new value of x here on the left, which we do by assignment, is equal to the previous value of x minus the value of the gradient. And this guy, minus eta times gradient of f of x, that there is our epsilon term from above, this part here. That's how we are changing x, negative eta gradient of f of x. So now why are we descending the gradient? Why are we using the negative gradient? It's because this makes the linear term as negative as possible. So I've drawn this here, the gold arrow, that's the direction of the gradient points. Remember, the gradient here is a vector, and so it has a direction. And so imagine this two-dimensional space here is all the directions that vectors point, and the gradient is this vector pointing in this direction. So this is a function that takes in two numbers and spits out a single number. So the question is, how does this function behave? How does this inner product function behave as I change epsilon? And that's what this circle here is meant to demonstrate. As I rotate epsilon around, then the arrow here is moving around this circle, and at each point it produces a particular value of this term here, this inner product term. So when it's close to the gradient, you get a really high value as indicated by this color scale here. And as we rotate around and go towards the middle, we get middling values. And as we go all the way towards the opposite direction, this term here becomes negative. So when we're pointing all the way in this direction represented by the blue arrow here, we get very negative values. So this function here shows you actually exactly how this function behaves as you spin epsilon around, say clockwise from gold to blue. And that blue variable there is -1 times the gradient. It's a gradient flip around. Just FYI, this function may look familiar. It's cosine. It's basically a scaled version of cosine depending on how big the vectors are. So the basic point of this slide is just that if we want to make this function here as negative as possible, we want to make the epsilon value equal to -1 times the gradient, and so point in this direction. So that makes this term here in the middle as negative as possible. And so long as this term on the right here is not bigger than epsilon, which we can guarantee because it's a little o, then that will make f at x plus epsilon smaller than f of x, and we will have made our machine learning algorithm perform better than it was performing before. And so gradient descent basically goes down the steepest slope. So I've drawn the gradients here on this topography here. So this is what the function maybe looked like for that previous example. We were looking at a single point and we were imagining the gradient points this way. How will our linear approximation behave as we rotate epsilon? Now we have a two-dimensional function here that produces a scalar value, and I've drawn here a couple places I've drawn what the gradient looks like. So the gradient points sort of up. The gradient goes uphill in the steepest direction possible. At the tops of hills, it's very clear you're at the top. There's nowhere to go that will make you go upwards. At the bottoms of valleys, the gradient is also once again 0. The way to think about it maybe is that at the bottom here, there's a whole bunch of directions you could go up in. There's no way to choose a particular direction to go up in. But it's maybe better, rather than thinking of gradients as going up or down slopes, it's maybe better to think in terms of these linear approximations. We should say that at this point, the best linear approximation is constant because the function's curving away in every direction, which is the same at the top here. Higher values of this function mean worse performance, so we want to descend gradients. We don't want to go up, we want to go down, so we flip them around. That's another way of thinking about what gradient descent does. So gradient descent tends to find the bottoms of valleys. In something like this, we would end up in one of these little divots here of bipolar gradient descent. We don't know where to start necessarily in machine learning and optimization in general. We often think of ourselves as starting at a random point, and so we end up randomly in one of these valleys. So to make that metaphor really direct, I got here the topography of my home state of California, which has a much more interesting topography than the state I was born in, which is Illinois. Very flat, not very interesting for gradient descent. California is much more interesting. So if you imagine you start somewhere in California here with these big mountains and this big central valley, this the Bay Area down here, another low-lying area, and you imagine, okay, what would happen if I just walked downhill? Because that's basically what gradient descent does. In most places that you start, you end up in this big area here, the Central Valley. If you pick a random part of California to start in, this basin here of the Central Valley is the place you would probably end up. The least likely place for you to end up is the highest point in California, Mount Whitney, because you have to land exactly on the top of Mount Whitney, and then if you're exactly at the top, then there's basically every direction is downhill, and you would go nowhere. The lowest place in California is actually not the place where you would end up, in most cases. The lowest place in California is actually this really deep cut in the middle of the Rocky Mountains here called Badwater Basin. And unlike the Central Valley, it is like very sharp. It goes down really quickly. The Central Valley is nice and sort of like gently sloping down from the mountains into this big flat area. And so Badwater Basin here is maybe where you think you'd like to end up if you're looking for the lowest point in California, but it's not where you're going to end up most of the time. Now what people have found is that gradient descent finds things like the Central Valley, and for realistic problems, you actually, things like Badwater Basin, these like sharp, deep, low divots are not where you want to end up. And the Central Valley is actually better. And this is one of the reasons why gradient descent has become basically the most popular algorithm for optimizing machine learning models over all kinds of other options that people consider for how to make algorithms. Like deep, low divots are not where you want to end up. And the Central Valley is actually better. And this like sharp, deep, low divots are not where you want to end up. And the Central Valley is actually better. And this is one of the reasons why gradient descent has become basically the most popular algorithm for optimizing
They weigh 1.5. We can use the line to predict that they will be 1.9 tall. So let's start with a simple data set. On the x-axis, we have weight. On the y